All right, let's get right into it. Today, we're jumping headfirst into one of the biggest, weirdest mysteries in all of physics: how a single particle can somehow be in two places at the same time. We're going to explore this through a tale of two totally mind-bending theories, each one challenging what we think reality even is.
This is it. This is the question that has kept physicists up at night for a solid century. I mean, think about it. How can one single, indivisible thing, like a photon of light, get in its own way? It sounds completely impossible, but, well, welcome to the quantum world. So here's the setup, the famous double-slit experiment. Picture this. You fire photons, one at a time, at a wall with two little slits in it. Logically, you'd expect to see just two bright bands on the detector screen behind it, right? One for each slit. But that's not what happens. Instead, you get this beautiful, striped interference pattern, the exact same kind you'd get from a wave. It's as if each little photon somehow went through both slits at the very same time and interfered with itself. So, what on earth is going on?
Okay, our first contender in explaining this madness comes from a theory called Bohmian mechanics. And it takes a really bold approach. It basically says, hey, maybe there's a hidden reality, a more intuitive one, bubbling just beneath all this quantum weirdness we see. The core idea here is the pilot wave. The best way to think about it is like a tiny little surfer on a huge invisible ocean. That surfer, that's our particle. It has a real, definite location at every single moment. But its journey, its path, is totally dictated by this much bigger pilot wave. So the particle itself doesn't go everywhere at once, not at all. It follows one specific path. But that path is carved out by a wave that does feel out all the possibilities. Now, for a long time, Bohm's theory had this one big problem, a real Achilles heel. It was non-relativistic. That means it worked great for slower particles like electrons, but it just completely fell apart when you try to describe photons, which, travel at the speed of light. But, and this is a big deal, recent breakthroughs have finally updated the theory. Scientists can now apply it to the very particles of light it once couldn't touch. And this is where it gets really, really cool. Researchers have actually been able to reconstruct what these predicted Bohmian paths would look like for single photons. You can see how the paths all cluster together where the interference pattern is bright, and they avoid the areas where it's dark. And here's the truly wild part. In some of those dark, empty regions, the math shows the photon's path actually becomes faster than light. Now, don't worry, this doesn't break causality or anything. No information is being sent, but it is a super strange feature of the theory. And in the end, when you look at all the paths together, their density perfectly, and I mean perfectly, recreates that interference pattern we see. So the crucial point to take away from Bohm's theory is this. The mystery is solved because you have two different actors in this play. The pilot wave is the thing that goes through both slits. That's what creates the interference. But the photon itself, it's just riding that wave, guided along one single, hidden but very real path. Okay, now take a deep breath, because we're about to switch gears to a completely different, and I would argue, even stranger explanation. This is Richard Feynman's path integral, and it tells us to just forget about a single path entirely. This right here is the revolutionary, mind-melting heart of Feynman's idea. To get from point A to point B, a photon doesn't take one path. Oh no, it takes every single possible path you can imagine, all at once. The path through the left slit, the right slit, a path that loops around Jupiter and back again, according to Feynman, they all happen. So how on earth can an infinity of paths create one single clean pattern? Well, it breaks down like this. Think of each path as a tiny little wave with a peak and a trough. That's its phase. Now, when the waves from all those really different, bizarre paths meet up, their peaks and troughs are all jumbled, and they just cancel each other out to nothing. But the waves from paths that are very similar, like the ones that go pretty much straight through the slits, they line up perfectly. Their peaks reinforce each other, and that's what creates the bright bands of the interference pattern that we actually see on the screen. So you see, in Feynman's view, the interference doesn't come from some physical pilot wave pushing things around. It's a purely mathematical interference. It's what happens when you add up the contributions, the amplitudes, from all of those little waves from every possible history. The weird paths cancel out, the most probable paths build each other up, and the math perfectly predicts the final pattern. So we've got two incredibly powerful explanations, and here's the kicker. They both arrive at the exact same correct answer. But, and this is a huge but, they paint fundamentally different, almost opposite, pictures of what reality is actually like. Let's put them head to head. In Bohm's world, a particle has one definite path. It's a deterministic reality underneath it all. In Feynman's world, you have an infinity of paths, and reality is really just a sum of all the possibilities. The strength of Bohm's theory is that it gives us an intuitive picture we can almost grasp, but the math gets really complicated. Feynman's math is just beautifully elegant, especially for photons, but the concept itself is completely abstract. It forces us to just throw out the whole idea of a particle having a single trajectory at all.
So you might be asking, all right, if they both predict the same thing, who cares? Why does it matter which one you choose? Well, the debate gets to the very core of what we even expect a scientific theory to be. This really isn't about one theory being right and the other being wrong, at least not yet. They're like two different toolkits for describing the universe, and the choice between them really comes down to your perspective, your philosophical taste even. Do you prefer a reality that feels intuitive, with real particles on real paths, even if the mechanics behind it are incredibly complex? Or do you prefer a reality that is mathematically beautiful and powerful, even if it's deeply abstract and defies every bit of our everyday intuition? And that leaves us with the ultimate question that these theories force us to ask ourselves. When we're not looking, is the universe following a single hidden script written by a pilot wave, or is it busy exploring every possible storyline, all at once, all the time? The answer is still out there, hiding in the quantum realm.